Good day, everyone. Today's topic is Vapnik Chervonenkis, it's shortly called VC dimension in machine learning. In machine learning, understanding the capacity and performance of a model is very critical. And one important concept that helps in this understanding is the Vapnik Chervonenkis VC dimension. The VC dimension measures the ability of a hypothesis space, the set of all possible models, to fit different patterns in a dataset. It was introduced by Vladimir Vapnik and Alexei Servonenkis. This concept plays a vital role in assessing the trade-off between model complexity and generalization. In simple terms, it helps us understand how well a model can balance learning from the training data and performing well on unseen data. Understanding VC dimension, the VC dimension revolves around the concept of shattering. To simplify, shattering means that a model or hypothesis class can perfectly separate or classify all possible patterns of a dataset within its capacity. What is shattering? So, what is shattering? A hypothesis class is said to be shatter a set of data points if, no matter how you label those points, example, assign them as positive or negative. The hypothesis class has a function that can correctly classify them. Example of shattering: imagine you have 2 points on a 2D plane. A straight line linear hypothesis can divide these 2 points in all possible way is based on their labels, example positive negative or negative positive. Hence the hypothesis class of a straight lines shatters these 2 points. However, for 3 points that form a triangle, a straight line cannot shatter them if their labels are mixed in a specific way. This simple idea of shattering helps us measure the capacity of a model. What is VC dimension? The VC dimension of a hypothesis class is the maximum number of points that the hypothesis class can shatter. If a model can shatter 3 points but not four, its VC dimension is 3. The VC dimension gives a way to quantify the complexity of a model. A higher VC dimensions means the model is more complex and can handle more complicated data patterns. Why is VC dimension important? Generalization models with too high a VC dimension may overfit, perform well on a training data but poorly on a unseen data. And simplicity, a model with a lower VC dimension may underfit, fail to capture the patterns in data. Mathematical foundations like the mathematical basis of the VC dimension allows us to analyze and understand the relationship between a model's complexity and its ability to generalize. Formal definition of VC dimension: that VC dimension of a hypothesis class $HS dollar is the largest number of data points that can be shattered by $HS. In other words, for a data set of size, if can shatter points but not points, the VC dimension of a $H dollar is $N dollar. Example, a straight line in 2D space has a VC dimension of 3. It can shatter any arrangements of 3 points, but it cannot shatter 4 points if one lies outside the plane formed by the others. VC dimension and model complexity. The VC dimension is directly tied to a model's complexity. Higher VC dimension indicates a more complex model capable of learning intricate patterns. Lower VC dimension suggests a simpler model with limited learning capacity. A balance between complexity and generalization. Overfitting. A model with a very high VC dimension may overfit, memorizing the training data instead of generalizing. So underfitting, like a model with a very low VC dimension may underfit, failing to capture the patterns in a data. The key theorems related to VC dimension are Sawyer's lemma. Sawyer's lemma provides a mathematical foundation for the relationship between the size of the dataset, VC dimension, and the number of possible classifications. It ensures that not every increase in the size of the dataset leads to increased model capacity. And generalization errors bound the VC dimensions also bounds the generalization error. helping us understand the model's performance on unseen data. Models with an appropriate VC dimension, not too high or low, often achieve better generalization. Bounds of VC dimension. The VC dimension plays a crucial role in providing theoretical guarantees about a model's performance. It helps in estimating two important aspects of machine learning: generalization errors and sample complexity. Generalization error and the VC dimension. The generalization error measures how well a model performs on unseen data. The VC dimension helps to bound this error using the following principle. A lower VC dimension indicates a simpler model, reducing the risk of overfitting but increasing the risk of underfitting. A higher VC dimension allows the model to fit complex data patterns but may lead to overfitting if not managed correctly. The VC dimension and error bound formula for a hypothesis class $h dollar uh, with VC dimension $ds d dollar and a data set of size $n dollar. The generalization error can be bounded as this formula indicates that the larger the data set larger the data set capital N dollar, the smaller the error, even for the models with the higher VC dimensions. Sample complexity and learning guarantees. The sample complexity refers to the minimum amount of data required for a model to learn effectively. The VC dimension provides insights into this requirement. A hypothesis class with a high VC dimension requires more data to avoid overfitting. Models with lower VC dimensions can generalize well with smaller datasets. Key insight: to ensure good performance, the number of training samples n should be proportional to the VC dimension d. This ensures that the model learns adequately without overfitting or underfitting. Key insight: to ensure good performance, the number of training samples n should be proportional to the VC dimension d. Capital N greater than or equal to d. This ensures that the model learns adequately without overfitting or underfitting. Applications of VC dimension. The VC dimension is not just a theoretical concept. It has practical application in evaluating and improving machine learning models. Below are some key areas where VC dimension plays a critical role, like the probably approximately correct pack learning. In pack learning, the VC dimension is used to measure how well a hypothesis class can generalize from a training data onto unseen data. So goal is to find a hypothesis that is approximately correct with high probability. Role of VC dimensions: it helps in determining the amount of data needed to achieve a desired level of accuracy. Models with appropriate VC dimensions are better suited for pack learning. A model selection: choosing the right model for a given task often involves finding the right balance between complexity and generalization. A model with a high VC dimension may overfit the data, while a model with a low VC dimension may underfit. The VC dimension provides a mathematical basis for comparing models and selecting the one that is most likely to generalize well. The capacity control: in machine learning, capacity control is about managing the complexity of a model to avoid overfitting or underfitting. By calculating the VC dimension, you can control the capacity of the hypothesis class. This ensures that the model has just the right level of complexity to handle the data effectively. Calculating VC dimensions. Calculating the VC dimension helps quantify the complexity of different hypothesis classes. The process involves understanding how many data points a model can perfectly classify or shatter. Let's explore how to calculate VC dimensions step by step. So, step-by-step method to calculate the VC dimension. So, identify the hypothesis class first. The first step is to define the set of functions or models under consideration, such as lines, circles, or decision trees. Test for shattering. Determine the maximum number of points that can classified in every possible ways using the hypothesis class. So if the hypothesis can separate all possible label combination of n points but fails for n plus 1, then the VC dimension is n. The formula verification is like ensure the hypothesis class satisfies the conditions for shattering up to small and points and using mathematical or visual proofs. So this is a Python code implementation for VC dimension. So I will, at the end of the video, I will show how this program can be run and how we can identify the points shattered and generate points and labels from that. And also we'll show how define points in 2D spaces, and the expected output will be like this. So So, conclusion is the BC dimension is a fundamental concept in machine learning that provides insight into the complexity and generalization capabilities of a hypothesis class. By understanding the ability of a model to shatter data points, the VC dimension helps balance overfitting and underfitting. So, these are the key takeaways. You can take it from this. Thank you. Bye. So in this code, you can see this is for VC finding the VC dimension, and of the linear classifier is 3. So for this, you have to import all these libraries, and also this is a function, the function to check if point are shatterable. And once you find it, next you have to do that, import the kernels and other stuff. And in one case, you are checking the any fitting error, consider it not shatterable, return false. And also next thing is generate points and labels uh, in the next check underscore vc underscore dimension of points. And the last one is we are checking the np array to achieve define points in 2D space to achieve a vc dimension of 3. So that is what we are trying to achieve here. And once we run this program, we'll get the output which is at the bottom, which is VC dimension of linear classifier is 3 for this particular array of points. Thank you.